Hello everybody. This is the second lecture of reinforcement learning, part of the course. And last class, if you everybody remembers, we covered how to train reward models and some reward models that don't need to be trained, basically the verifiable rewards. And today what we will look into is how do we use these reward models, and we'll look at methods where you don't need to train anything, just use the reward model directly, which is very simple. And we'll also look at methods where you train a policy to use the reward model to generate outputs with high reward. We'll look at so this is the top. These are the topics that we are going to cover today. And slowly we are going to build up towards PPO, or proximal policy optimization, which so PPO has a lot of different aspects that cannot be covered in one class. There are a lot of different things. We'll cover two things that will reach towards PPO, and the remaining will be covered in the next class, where we will also talk about GRPO. Okay, so we'll look at the best of n policy, which does not require any training. It's simply you take the language model, or whatever the starting policy you have a reward model, and you sample a bunch of outputs, pick the one with the highest reward. So that is a very simple thing. Then we will look at what the reward maximization objective looks like, and we'll cover two algorithms: the vanilla policy gradient algorithm, and the second one is the Actor-Critic, which is a family of algorithms. It's not one algorithm, it's a bunch of different algorithms. And we'll see what the general picture of the Actor-Critic algorithms is. We'll not look at all possible Actor-Critic. There are a huge number of them. PPO is an example of Actor-Critic that we will see in the next lecture. So let's start with the best of n policy. So best of n policy is very simple, that you have a reward model, you have a reference model, starting policy, and you want to generate outputs that have high reward as dictated by the reward model. So how do you do that? You generate multiple outputs from your starting policy or the base policy. We also call it the reference policy, and it is generally an instruction tuned model that when we start aligning, there is generally a instruction tuned model, and recently people have started using pre-trained models, also pre-trained base models also as starting policy. Okay, so we generate multiple outputs from the starting policy, whatever it is. You score each of them using the reward function, and you pick the one with the highest reward. So pretty simple. There's not much in the best of n policy, and whatever is the highest reward, you return. And this is just a picture explaining the same, that you have a prompt, something like write a poem, and you have a reference policy, and you sample a bunch of outputs from the reference policy, and then you score each of those outputs using the reward model, and then pick the one with the highest reward. So yeah. Right. So we are not. This is. I mean, you can train it. Right now, what I was mentioning here is that this requires no training. Basically, you have a reference policy. Reference policy can be an instruction tuned model. You have trained on a bunch of. So Professor Tanmay covered instruction tuning. So you will be familiar with given input output pairs, how to get an instruction tuned model, right? So if you have an instruction tuned model like Llama instruct model or any of the instruct models, you can sample multiple outputs from that and pick the one with the highest reward. Now, if you have to train it, let's say you want to train it, you can train with this highest reward output. You can do an SFT, an instruction or supervised fine tuning, on top of this highest reward output. That's one way to train the model. But here I was just talking about picking the simple way. There you are just using the reward model for ranking, but not for training. So the advantage is that you don't require any training here. The disadvantage is that your inference time blows up, right? Because you have to sample a lot of different outputs and then pick the one with the highest reward. And another disadvantage is that you cannot do iterative improvement. What I mean by iterative improvement is that suppose you had a prompt, you generated a bunch of output, picked the highest reward. Now in the next step you had a, let's say, similar prompt, right? But not exactly same. Maybe it was write a poem about cow, and the second prompt is write a poem about horse. Now the advantage of our reinforcement learning is that you can use the information in prompt 1 to get, I mean, if you have trained using prompt 1, you will get your outputs for prompt 2 will also improve, right? But if you're just picking the one with the highest reward, then there's no information getting transferred from one prompt to another, right? You will again have to sample 8 or 16 or 32 outputs, pick the one with the highest reward. So it cannot get better iteratively. So then you cannot do this during inference time. You can only you cannot basically use the best of n policy during inference time. I mean, because you will not have a reward model basically, right? So we will look at the reward maximization objective, which probably is more interesting and which is what people use. We'll try to frame this objective first, and then we will look at 2 algorithms to maximize this objective. So what is the reward maximization objective? The task is same. Given you are given a base policy, you are given a reward model, and you want to generate outputs with high rewards. So now you want to train the base policy. So when I say base policy, we should think of an instruction tuned language model, right? So the task is that you want to take this base policy and use the reward model somehow to train this base policy so that it generates high reward outputs. Another point is that generating high reward outputs is not sufficient. And we'll talk about why it is not sufficient. So, but the idea is that your reward model that you're going to train with, it's not a perfect reward model. It has been trained on some preference data that was available to you. You just use that to train the reward model. So when you train the reward model, it also picks up a lot of noise. It also picks present in the, so it, for example, if your data looked like where longer responses had higher reward, were preferred over shorter responses in a lot of cases, then the model might simply pick up that reward model might simply give high reward to very long outputs. But there are lots of different noises that the reward model can. The reward model may end up focusing on a single specific token. It may say that, okay, if this token is present, I will give high reward. And the reason is that because you're not trained in all possible data, you're trained in on a very small subset of data, and now you're expecting it to generalize to everything, right? So you don't want to just maximize the output with the highest, maximize or generate output with the highest reward. What you want to do is to be also remain close to what your starting point was. If your starting point was, let's say, the starting point is an instruction tuned language model, it generates reasonably good outputs, let's assume, right? So if it's a good approximation of what the sentences should look like, if it's a good distribution of what the natural language sentences should look like, then here what you're saying is that don't deviate too much from what your starting point is. The output should still look like reasonable natural language and should be reasonable outputs for the given prompt. So these are the 2 objectives that we try to maximize together. So I was already mentioned why should we care about closeness to the reference policy. The reward, as I said, so this is saying the exactly same thing, that reward model have been trained to score only selected outputs, and it may, if you try to maximize the reward model, the output that maximize the reward model will not look like natural language at all. It will look very weird actually. So you don't want to simply maximize the reward model unless if it is a perfect reward model somehow. If you, I don't think there is any perfect reward model, but so you don't want to hack the reward model, and basically that's called reward hacking. If you end up maximizing the reward, which has, so if your model ends up generating very high reward output, but they don't make any sense at all, it's called reward hacking. So yeah, so reward another point to note is that you may have multiple correct outputs, and if you do reward maximization, what will happen is the model will overfit to the highest reward output, and maybe you want diversity in the output. Generally, diversity is a preferable thing to have. So that's another reason why we add this closeness to the reference policy as another loss function. Okay. So there are 2 things, as I mentioned. One is the reward maximization part, and yeah. So one is the reward maximization part, and the other one is staying close to the reference policy. So what does reward maximization mean? That I want my policy to be such that if I sample a bunch of outputs and score them using the reward model, the average reward of those outputs should be high. So I want to have this policy pi theta. So this is pi theta, that is the trainable part. This is what we want to train, right? And we want it to train in such a way that if I sample, let's say, a bunch of outputs, or if I sample a bunch of outputs from the policy and take the compute the expected reward. This is the expected reward, right? If you want to, this is how you write expectation. So if, this quantity should be high. I want to maximize this quantity. Does it make sense? Okay. Is there any confusion about this expectation? Okay. So I want to train theta such that this expectation is high. How do you approximate an expectation? Yeah, you can basically, it's called Monte Carlo sampling. You just sample a bunch of outputs. Monte Carlo is just a fancy name where you, it means that if you have to approximate an expectation, you just sample from the policy and compute the average reward. Where y1 to yn, these samples, where do they come from? Pi theta y given x. So this is the reward maximization objective. The other objective is that you want to stay close to the reference policy. How do we capture the closeness to reference policy? So any idea how do we capture the closeness to reference policy? KL divergence, yes. So the next term is the KL divergence between the policy that I am training and the reference policy. And the KL divergence can also be written as an expectation. So what will this look like? Expectation under the policy log ratio of probabilities, pi theta y given x, pi ref y given x. I don't know if is it visible to everybody? Okay. So does this equation make sense, this expectation, or is there any confusion about this KL divergence term? Anybody? Okay, if you are looking for KL divergence for the first time, probably this will not look very familiar, but for now you can assume that this is what the KL divergence looks like between the policy pi theta and the reference policy. So this you want to maximize or minimize? Minimize. So we want to minimize this quantity. So the final objective looks like a combination of the previous reward maximization objective that we saw here and the KL divergence objective that you saw here. So this is the final object. So this is how we combine the objective. We take the policy, sample the outputs from the policy. For each output, we pass it through the reward model and get the reward of each output. Similarly, we pass for each of the output to compute the log probability under the pi theta, the policy that we are training, and log probability under the reference policy, pi ref. And we get both of these quantities and compute the difference, log pi theta minus log pi ref. That's what this KLR term that you see here is. It's basically log of pi theta by pi ref. Okay. And then you multiply. So now how much weight to give to the KL divergence and how much weight to give to the reward maximization, that is controlled by the beta term. So this controls the weight that I should give to the KL divergence term and the weight that I should give to the reward maximization term. And I multiply the KL by beta and then compute the difference between these two quantities. So I want to maximize this quantity and I want to minimize this quantity. So that's why I will look at the difference of these two quantities, and that will give me the objective that I want to train. Okay, so let's write both the objectives again. The reward maximization objective was that I sample from the policy that I am training and compute the expected reward. This is the reward maximization objective. The KL divergence can be written as again sample from the policy that I am training and look at the log probability ratio between pi theta and pi ref and take the average. That is your KL divergence. And how do you combine them? You just add, take this term, the reward maximization term, you take the KL term. So expectation I can take common between the two, right? And you multiply the KL term with beta. And you get the combined objective. So this is how you will approximate the this is how the combined objective will look like. You will have a policy that you want to train, sample a bunch of outputs, and each of the output you will send to the reward model, and each of the output you will send it to the reference model to get this ratio, log probability ratio. And the difference between the reward and the log probability ratio is scaled by beta. This you can think of as a regularized reward. Oh, I've already written it below. Regularized reward. And regularized, so we don't want to just maximize the reward of the output. We don't just want outputs with high reward. Now we are saying that we want outputs for which regularized reward is high. So we are trying to maximize the regularized reward. Does that make sense? Also, so let's say this sampling process was differentiable, and this reward model, everything was, let's say, differentiable. Okay, reward model is generally a language model, so this is often differentiable. This is also differentiable. If this sampling process was differentiable, let's say this particular part, then I could, in principle, do a forward pass, compute this average, and do the backward pass. I mean, so if you have a network which is differentiable from end to end, you can do back propagation and you don't need to do anything. You can just do the forward pass and compute the loss function, whatever it is, assuming that the loss function is a differentiable function of the parameters that you want to train, and do the backward pass. But this part is not differentiable, the sampling part, and that's where all the algorithms come into the picture. So if any of you are familiar with variational autoencoder, there also a sampling is involved, right? You have is anybody familiar with variational autoencoders? Okay, somewhat. Maybe not a lot of people. So when the sampling process is differentiable and the loss function is differentiable, then you can backpropagate the gradient. If it is not, then you have to put some more effort to make this work. Okay. So now we'll look at the first algorithm, which is vanilla policy gradient, and we'll see how vanilla policy gradient algorithm looks like. So this has three parts. We first will talk about the reinforced gradient estimator, how to estimate the gradient of the loss function that we are trying to maximize or minimize, and then we'll look at the problem of high variance, and finally we will have the vanilla policy gradient algorithm. Okay, so we have the maximization objective. How do we go about maximizing it? So when you have anything that you want to maximize or anything when you want to optimize, the first thing to do is, since I cannot do differentiable backward path end to end, the first thing to do is to compute the gradient. And that the gradient estimate of this objective is called the reinforced gradient estimate. We'll see what is, why is it a spatial gradient? And if we can, once we can get the gradient of the objective that we are trying to maximize, then we can just use any of these gradient based optimization algorithms. So if you take ADAM, AdaGrad, SGD, all they need is your gradient per batch, and if once you give them this is the gradient per batch, you can just run these algorithms, optimization algorithm, and they will update the weights, and you can keep on doing, and your training will be done. So all you need is how to compute the gradient. No. This is so if sampling is differentiable, then you don't need any basic. Then you just need to compute the loss function and do loss dot backward, and automatically gradient. So just the chain rule is sufficient in that case. But only when, because here sampling is not differentiable, we cannot use the chain rule to compute the gradient of everything. Okay. So we'll see how to compute the gradient here. Okay, so gradient of the expected reward. Can I take this gradient inside the expectation here? Can I take the gradient inside? I cannot take the gradient actually, and the reason is that the expectation is over the policy itself. So let me expand the expectations. I can write the expectation, not approximate it. If I can write the expectation exactly as follows: y belonging to the list of all outputs, pi theta right. I've just expanded, no approximation here so far, and I can take the gradient inside, because see this a summation does not depend on theta. This summation is fine, and I can write it as and this is the quantity that we want to approximate. We want an estimate for this quantity. This is exact. What we want is how to estimate this quantity using samples. That's the question that we are trying to answer. Okay. So exact computation is intractable, and the reason is that this summation, this space is actually can be the space of all possible sentences in the world. This space can be infinite. So we want to approximate it using samples. Now, if I just give you this expression and ask you to approximate it, it's tough. The reason, see, what we do know is that how to approximate an expectation. If you have an expectation of a function, you can approximate it. But this quantity does not look like an expectation to me. This quantity that you see here, this is not an expectation. This is a gradient of an expectation. So somehow I have to make it look like an expectation, because I know how to approximate an expectation. So I want it to look like this. This is how I want it to look. So instead of gradient theta pi theta, I want pi theta times something. Does that make sense? So why do we want it to look like an expectation? Yeah, we can approximate an expectation. So if I can do that, so that's where the next trick comes from, that how do I change this quantity to something like this? So that's called the log derivative trick, that if you have to take the gradient of a log, what does the gradient of a log look like? If I compute this gradient, what will it look like? Yeah, so 1 by pi theta Okay. Which means that this quantity can be written as gradient of theta pi theta y given x is equal to pi theta times the gradient of log. And now we can plug it back in the previous equation we had. So let's see what the previous equation was. The first equation that we have. We can replace this term that we have here, by the log derivative trick that we applied. So what will happen to this summation? Let's write summation y belonging to y gradient theta pi theta So the first thing that we'll do is we'll replace this gradient theta by pi theta times the gradient of the, this quantity basically, log pi theta. Is that fine with everybody? And now if you look at this quantity as something, now does this look like an expectation? So now I can write it as expectation y coming from pi theta rxy into gradient theta. Okay. So now I can approximate the expectation using samples. This was the whole reason why we did this trick. And now I can estimate the gradient using samples. So how will I estimate the gradient? Now, so again, let's say the prompt is write a poem. I will use the current policy. So this is what we are training right now. Always remember that this is what we are trying to train. And we will sample from the policy that we are training. We'll pass those samples to the reward model. We'll pass those samples to the gradient computer, whatever the, basically we'll do a backward pass. So this is generally done during the backward pass of log pi theta y given x computation. So if you are computing log pi theta y given x for a sample and you do the backward pass, you will get this gradient quantity. So you get this gradient, you get the reward, you multiply by the 2 and just average, and that will give you the reinforced gradient estimate. And then you can use this reinforced gradient estimate for training. So if I have to write the estimation, let's say I have y1 to yn, which are samples coming from the policy. What will be my reinforced gradient estimate look like? 1 over n summation I equal to 1 to n r x y I times gradient theta log pi theta y I given x. So this is your reinforced gradient estimate, and this you can use for training. So this is the first part of moving towards PPO, deriving the reinforced gradient estimate. Now this estimate is actually quite noisy. Why is it noisy? So if I had chosen a different set of samples, I would have gotten a different gradient. See, when you are doing instruction tuning, your input is fixed, output is fixed, and your gradient is always fixed. No matter what you do, you will always get the same gradient. Maybe dropout or something will change the gradient a little bit, but there won't be a huge amount of variation. But when you are trying to estimate the gradient in reinforcement learning, the number of outputs, so the gradient estimate always depends on what outputs get sampled. Change the outputs that got sampled and you will get a different estimator. So we'll see how to deal with the noisiness of this gradient estimate. Okay. We'll see this how to estimate how to deal with the noisiness, but for now let's expand the gradient in terms of tokens. So why are we doing expansion? So this is just to show how when you are implementing it, let's say in code, how will this look like. So let's say your y is a response actually contains of the tokens a1 to am. Okay, so this will be rx comma y. So I can expand the log probability of under the policy of first response y of an output y in terms of tokens, because it is an autoregressive model. How do I expand this? What will it become? Even does anybody have any idea what becomes of the log probability of y if I expand? No, it will just expand in terms of its token summation I equal to 1 to m log pi theta of ai. Yeah, I should have used the term j equal to 1 term. Let's say j given a1 to aj minus 1 and x. So the log probability of output of a sequence of tokens is just the sum of the log probability of those individual tokens, conditioned on everything that comes before. Okay, and now if you put gradient inside, this will be summation j equal to 1 to m gradient of the log of pi theta actually yeah. So or you can let me just sorry you can put this rxy inside, although it does not make much difference. I'll just put this rxy inside. I will call this quantity that I'm conditioning on all the past tokens, including the prompt and the tokens that you have generated so far. Yeah, this is the state. So I will call this as sj. Okay. Okay. And so if you have to implement it using a language model, what you will do is you will take the prompt. These are the prompt. You will take whatever output got generated output, and you will pass all these tokens through the policy. And for the tokens that got generated, only for the tokens that were generated, you will compute the log probability of each of the token given the past, right? So log probability of Taj given the prompt, log probability of Mahal given prompt and Taj, log probability of is given prompt, Taj, Mahal, and so on. You will compute the log probability of each token. You will sum up these multiply them with the reward of the total reward of the output. This includes the reward that comes from the reward model and the reward that comes from the KL, negative beta KL, right? So it might come from reward model or may come from negative beta KL. And you will sum up the reward, sum up these reward time log probabilities, and then you will backpropagate. And that will give you the reinforced gradient estimate. Okay. So this is the algorithm. You sample, you will repeat this process until you converge. You will sample a bunch of prompts from the data, and for each prompt you will get some outputs. You can use VLM, SGLang, whatever framework you want to get sample outputs from the policy. This is the policy that you are training. For each output, compute the reward, compute the log probability of the output under the policy that you are training, and also you will probably need okay. So this reward may include both of the things, the reward model and the negative KL. And now to get the loss, you will multiply these two quantities, reward times log probability for each output, and you will average across the outputs. And then you will back propagate, that will compute the gradient, and then you can train. So it's pretty straightforward. But as I mentioned that this is gradient estimate is very noisy, so it's very it does not if you train using this gradient estimator, it will diverge, the training will diverge very fast. So we have to somehow reduce the noise, and we'll see different steps to reduce the noise. The first step is to do a baseline subtraction. So what is baseline? Let's say you have two random variables, one that can take values between 95 and 105, and can take integer values. Only I should have mentioned it's only integer. Okay. So it's a discrete random variable. Yeah. And the other random variable can take only two values, +1 and -1. Let's say. So if I sample from the product of these two random variables, x times y, what will the samples look like? They might be either very positive or very negative. Very positive or very negative, right? In other words, the difference between the samples can be very huge. And mathematically, if you want to say this, you can say the variance across these numbers is going to be very high, right? So, but if you had subtracted, if you have taken the mean of the x and subtracted, so 100 is the mean of x, this is the expected value of x. I'm guessing expectation will be that only, but I'm not sure. Somewhere around 100 it will look like, right? So if you had subtracted the mean of the random variable x and then multiplied by y and then sampled from that quantity, then how will the numbers look like? They will look like -5, 4. I mean, the difference between these numbers will not be as huge as in the first case. Or in other words, the variance is low. So that means that if you center one of the random variables or one of the random variables, if you center them somehow, then you can reduce the variance of the overall thing that you're trying to estimate. And that's what we are going to do next. So when we are computing the reinforced gradient estimate, we are multiplying two quantities, the reward of each output and the gradient of log probability, and then we do the average, right? So that can have very high variance, but one way to reduce variance, and this is the simplest way, is to compute the average of the reward and subtract the average of the, so let's say you had sampled 8 outputs. You can take the average across those 8 outputs and subtract the average from each reward and then multiply by the gradient. Do that, then the variance of the reinforced gradient estimate reduces a little bit. I mean, it's not a perfect way of reducing the variance, but it will reduce to some extent. And what will the new reinforced gradient estimate look like once you subtract this baseline? So it will be 1. So let's say again we assume y1 to yn are the samples. So 1 over n summation I equal to 1 to n. So instead of reward, now you'll have rx yi minus r bar x. So r bar does not depend on the outputs, right? It only depends on the prompt because it's average across the outputs. Times gradient so sometimes I will use r hat to refer to this, the reward minus baseline. I will use r hat to refer to this quantity, or sometimes I will also use r to refer to this quantity. We can assume that it's already, you have subtracted the mean. Another thing is that this mean need not be just over the outputs of the given prompt. You can take the mean across the entire batch. So let's say you have 10 prompts in a batch and 10 outputs per prompt. So across all those 100 outputs, you can take the mean. So if you do that, you will get something similar to the GRP algorithm, which we will discuss in the next class. Sorry. Yeah, but no. So yeah. So if you subtract, sorry, my bad. If you just subtract the mean for outputs for a given prompt, then you'll get something similar to GRP algorithm. If you do the compute the mean across the entire batch, then it's not GRPO. It's basically standard reinforce baseline reinforcement. So this, if you are, so if you have this baseline, there will be a small modification to the vanilla policy gradient algorithm, and now the reward computation will be followed by the computation of the average reward that you will subtract from the reward of each output, and then that you can use to compute the loss. Okay, so this finishes the reinforce the policy gradient part of it. Now we'll move towards actor-critic algorithms, which is the second step before building towards PPO. So let's look at the reinforced gradient estimate again. The way we computed the reinforced gradient estimate is that we took the prompt, we took the output, we passed them to the policy, we got the log probability of each token, multiplied the log probability by the reward of the entire output. Now if you look at the first token, Taj, let's look at this token. What is the loss associated with this particular token, or what is the objective associated with this particular token? It's just this quantity, reward times log probability of Taj, right? Now if let's say so this question is very Taj Mahal and the response is Taj Mahal is in Agra, so the reward is probably going to be positive, right? Because the response is correct, so reward is going to be +1. So that means what the objective is saying, that this reward will be +1 times log probability of Taj. So if I use this objective for training, it will say, okay, Taj is the correct token, it has a positive reward, so let me increase the probability of this token. But this response could have been something else. This response could have been Taj Mahal is in Paris, so the first token is still Taj, but now the response is wrong, which means the reward will be negative. And now if I compute the objective again, this will be -1 times log probability of Taj, and effectively what I'm saying, decrease the probability of. So in one case I'm telling the model increase the probability of Taj, and in other case I'm telling the model decrease the probability of the Taj. But the point is that Taj is not contributing to the correctness, right? The only thing that is contributing to the correctness is this last token, whether it's Agra or Paris or something, right? So this is the problem of credit assignment, that if this response gets a positive reward, which tokens in this response actually resulted in the positive reward, and if this response gets a negative reward, which tokens in the response actually resulted in negative reward. That's credit assignment. So this is exactly what I said, that if you are generating Taj Mahal is in Paris, you will get a negative reward, and if you are generating Taj Mahal is in Agra, you are getting positive reward. And it's not clear to the model whether to increase the probability of the word Taj or to decrease the probability. So ideally, how do you solve this problem? Let's say you lived in an ideal world where you had infinite compute and do anything. So what would you do in that case? You can probably take the word Taj and generate all possible sequences from the policy that follow this word Taj. So you can fix the word till Taj, and you can keep on generating from that point until the sentence ends, and generate infinite number of sequences. And you can then take the average of reward for all those sequences, and I'm guessing the average reward will come out to be 0, because let's say there are lots of possibilities, some will be positive, some will be negative. So it will turn out that if you compute the reward of all possible sequences that can be generated from Taj, that expected reward may be 0, right? Because Taj does not control the correctness of the response, right? So that's what is called the Q function. Q function is that if I generate Taj and then if I continue the policy, what is my expected reward what is the expected reward that I will get? That's your Q function. So it's an average over all possible continuations that follow Taj using the policy. So I should mention that Q function is always a function of the policy. So using the policy. And if you use this Q function, that gives you a very stable estimate for learning, because if you can tell whether to increase or decrease exactly with that, does not depend on the sample that you are going to generate, then training becomes stable. Also, this expected reward, okay, I have used the word discounted here, which I will talk about later. This cumulative reward after a given time is also referred to as reward to go, or it's also referred to as return. So there are these terms that are sometimes used interchangeably, reward to go and return. And yeah, so more formal definition of Q function. Q function is the if you are in state S and if you have taken action A. So state is basically all the tokens so far, action is whatever token you generate just now. So if you are in state S and taken action A, then the Q function is the reward of the current state and action plus if you continue from that point onwards. So I am assuming that that time is t. Let's assume that we are at time step t, then it's gamma times, I will talk about what gamma is. St plus 1 at plus 1 plus gamma square t plus 2 and so on until you encounter the end of text in case of language, and expectation over this, expectation of this quantity. So these, think of these at plus 1 and at plus 2 are the tokens that follow the word Taj, and st plus 1 is all the tokens previous to it. Okay, so gamma square times reward. Yeah, so actually gamma and R looks a bit similar, so I will make this slightly different. Okay, and this expectation is over these tokens that you generate, at plus 1, at plus 2 and so on. So you keep on you sample tokens, compute the reward of the future. So in the case of language model, you generally get reward at the end. So you can think that I generate starting with Taj, I generate first sequence, get the reward, second sequence, get the reward, third sequence, get the reward, and then take the average. That's your Q function. Okay. Why? Okay, also this discounting is there. So why do we need this discounting? So this discounting is something that is used when you're doing policy gradient or PPO in games, or when you're doing it for robotics. And the reason is that suppose you are trying to train a robot, and it took, let's say it moved its hand from here to here, and finally in the end it achieved it got a different reward at different time steps. So the point is that the rewards that it got immediately after taking some action, those are more relevant for that action. I mean, so the action could have influenced future rewards also, but the immediate reward that it got is probably more relevant to the action. And the reward that it got, let's say after 1000 time steps of taking action, probably they're not very relevant. So that's why this discounting factor is there. In language models, generally we set the discounting factor to 1. We don't worry about the discounting factor. Okay, so let's look at, so what does the Q function look like for a language model? You have the prompt and you have the partial response, which is the word Taj, or partial output. And you got a reward for, you probably generated the word here. So generated the word is here, and you got a reward of 0 here, because generally you get a reward at the end of generation. So now the Q function is the reward, this quantity. Now you continue from at this point. So after you will feed is again, you will get some other output and keep on doing this. So you will keep on feeding this token step by step. Whatever reward you get, you accumulate it, and if you do this multiple times and average, that will be your Q function. So starting from a point, just compute what are possible continuations and get the reward and average. And this quantity also known as the reward to go. The given a particular time step, whatever reward of tokens that you get after that point, that's called the reward to go. So again, in language models, this can simply be the reward of the entire response because you are getting reward at the end.
Can you represent some successful words? Can you give any relation between parts to be assigned as per the successful words?
So we'll come. So that's what we are trying to do. We are trying to reach a point where we can assign tokens different reward. That's what the Q function is. So Q function is for a particular token is that if you generate all possible sequence from that token and take the average reward. So it's going to be different for each token. So for example, for the word Taj, it might be 0 because the question is where is Taj Mahal. Then the word Taj does not affect the reward. It might or not. So I think that's what you want, right? That's what you're saying. That how do we assign different tokens, different reward, right? How do we decide where? And so this Q function does that job. Q function says that all possible sequences at this point, compute them, take the average reward, and that's what the. So it's a replacement for a reward. You can think, right? And now we cannot generate all possible sequence, so we'll see how to approximate it. But right now you can assume somehow magically you can get this Q function. Somehow you can compute the average reward for all possible sequences starting from that point using the policy, sampled from the policy. So if you can somehow get that quantity, then the reinforced gradient estimate will look something like this. You feed the prompt. This is your prompt. Then this is the output that got generated. And now somehow magically you also have the Q function at each token. So instead of multiplying the reward with the log probability of the token as we were doing for reinforced gradient estimate, what we'll do is multiply the Q function with the log probability of each token, sum up the log probabilities and do a backward pass, and that will give me the give me a gradient estimate that I can use with Adam or whatever optimizer to update the weights. Does that make sense? So I've just replaced the reward with the Q function. Okay. Okay. So Q functions are so just like for the rewards, what we did was we subtracted a baseline to make the reduce the variance, right? See, because why do we still have variance? Because we are still sampling outputs to be able to generate the gradient, right? So as long as you're sampling, you will always have variance across the gradient estimates. Different samples will give you different gradient. That's your variance, right? So just like we did it for the case of reward, we subtracted an average reward. Can we do it for the Q function also? And the idea is very simple that so in the case of reward, we computed the expected reward and then we subtracted from the reward of each output. In the case of Q function, we will compute the expected value of Q function at a given state. So now the Q function is different. So we'll at each time step, we'll compute the expected Q function, which is called the value function. So value function is the expected value of Q function at a given state. And that we will subtract from the Q function to give us the advantage function. So so Q function captures that, okay, if I am at a particular state and a particular token, and if I keep on sampling according to the policy, what is the average reward I will get? The value function says that if I am at a particular state, I have not taken any action, I am at a particular state. Now if I compute the average reward, I will sample according to policy and compute the average reward. What is the average reward I will get? So value function does not depend on action. Q function depends on the action. So think of it, value function as a baseline. It's saying that, okay, I have not taken any action. Now what is the average reward I will get? And Q function is after if I have taken a particular action, what is the average reward I will get? And the difference between those two quantities, basically it captures how good the action was. So if the action was very good compared to the other actions, that I could have taken at that point. So if the action was very good, this advantage is going to be high, right? So it captures the contribution of one specific action.
example, when we do a task,
Right. Right. So the queue function, if you let's say if you have not generated any token and you are generating if you are generating Taj, the queue function is that given that you have generated Taj, what is the expected reward that you will get? And value function is that before you generated Taj. Right. Yeah, so include all possible tokens that you could have generated. What is the average reward you would have get? That is the difference between queue and value function. Okay, so we are reaching towards the end of the slides. So now if you have to do reinforce with advantage function, again magically if you assume that you are given a queue function, you are given a value function, you can compute the advantage function for each token, and you could do the same gradient estimation computation that you did earlier. Take each token of the output, pass it through the L policy, compute the log probability, multiply by the advantage for each token, and sum, and then you can backpropagate. That will give you the reinforced gradient estimation with advantage function. Okay. The last part is how do I estimate? So now we don't magically have Q and value function. So how do I estimate this? So when you are doing reinforcement learning for language models, Q function is generally estimated with a single sample. That is, you generated an output by A1 to AN or A0 to AT. This is the output that you generated. Then Q function, instead of saying that all possible sequences that could have originated at a point, I would say only for this sequence, what is the reward to go? What is the at each time step? What is the reward to go? Which is the reward of the entire response? So at each token, basically, you will have the reward of the entire response, and that will be a Q function because it's the future reward, right? So Q function is generally estimated using single sample. The value function is estimated by training a neural network. So okay, let me write down the Q function. So if you have sampled this particular output Y, the Q function at any given time st comma at, st is the past tokens, at is the token that you're generating at time step t. This is given by the reward of this token plus all the future rewards. So I will assume gamma equal to 1 for now. So reward of st plus 1, at plus 1 until you encounter the end of text. st, sorry. st comma at. So this is your Q function estimated using just one response. Okay. The value function is estimated by training a neural network. So what you do is you train a neural network that you sample outputs from the policy, compute this quantity again for each of the outputs, and you train a network to minimize the. So you have a network which gives you this value v. So this network, let's say v5 st. So you minimize the difference between this v5 st and the reward of the entire sequence that you got. So this quantity STAT plus ST plus 1 and so on. You train a network to minimize this quantity and do it for all tokens. So 1 over capital T summation T equal to 0 to T. So at each point, so you have a network which takes each token and outputs a number. And this is how the network looks like. Generally, the policy itself is modified to also predict the value function. So at each time step in the policy, you have a linear layer, which basically this is the pre-logit layer, or the last layer before you have the unembedding layer. So you have this is your unembedding layer, this is your unembedding layer, which is anyway there in the policy. You add one more layer, whose output is only one dimensional, and you'd say that okay, this particular layer is what I want to train to predict value. So this is your value function, and you train this value function at time step 0. You will train it to predict the reward of the entire sequence. At time step 1, you will train to predict the reward of the sequence from this point onward. So if the reward of the entire sequence is given only at the end, it doesn't make a difference. But let's say you have KL terms, so there is a reward at each token also, or you have some other reward model which can give reward, intermediate reward also. So in that case, you minimize the squared error between the value function at each time step and the reward that you get from that point onwards. So this, so the set of algorithms, so this is called the critic. We call this network as a critic. Why? Because if you look at the algorithm, the way we are training, we have the actor, which is parameterized by pi theta, which parameterized by theta. The LLM policy is referred to as the actor, which takes, basically that is the one that taking actions. Now critic is the one who is so you train this actor by minimizing the expected maximizing the expected reward, and you train the critic to minimize the squared error from the reward. So you're training the policy to generate outputs that will have higher reward than what the value. So value function is your average reward. So you're training the policy to generate outputs that will have higher function than what the value function gives at a point, and you are training the value function to be able to predict that reward, to be able to predict reward back. So it's like adversarial training, if you guys are familiar with it. You're training your generator to give outputs that are higher reward than the value function. And then you're training the critic to minimize the squared error. So this is a family of algorithms. There are a bunch of algorithms that follow this pattern of training the policy and training the critic, and this family of algorithms includes PPO, which we will cover in the next class. Okay.